Hello and welcome to our channel again. Suraj here, and today we are going to start our topic on the capacitor and the dielectrics. So what is capacitor and what is capacitance we are going to discuss in this video, and this is the lecture number 1 on this particular topic. So in today's video, we are going to discuss about it, what is capacitor, capacitance, and the capacitance of the two parallel plates. This is a very famous parallel plates problem there in the JEE exam also. So it carries a very high weightage in JEE exam. That's why the parallel plate capacitor is a very important topic. So in this video, we are going to discuss about these introductions and the basics of the parallel plate capacitor. And in next video, maybe we are going to discuss about the potential energy of a two parallel plate capacitors. There is a two parallel plate capacitor, find out the potential energy between them, and also different types of the capacitor also. So let's start our today's video on the capacitors and the dielectrics. So let's start our today's topic with an example. So there are different types of the electrical equipments there, like there is a fan. So if I imagine a fan, and you know that when you want to turn on the fan, so let's suppose you have fan there, okay, and then this is your typical fan, and you know that when you have to start our different types of the electrical equipments, it requires extra amount of electrical energy to turn on the electrical equipments like our fan. So our typical electric current cannot provide that amount of electrical energy, so there is a capacitor in the fan that gives us the electrical energy boost to our fans to on this. And that's why the capacitor is very important. It stores the electrical energy, and its uses is when you have to start your electrical appliances, like your fan is there, your flash bulb is there. So the normal electric current cannot provide that much amount of electrical energy to turn on the electrical appliances. So to turn on your electrical appliances like your fan, you have to provide your extra energy, and that is provided by the capacitor. And that's why capacitors is a very important uses in different types of electrical equipments. In every electrical equipments you will find out capacitor, like in fan is there, in flash bulb, and I think in flashlight also there is a capacitor. That's why capacitor is very important in learning about the different types of the electrical equipments. Now let's some of the more practical scenario related to the capacitor. How can I make a capacitor, or what is in the capacitor? So we all know what is capacitor. It is an electrical device that stores the electrical energy. So in the typical thing, the capacitor stores the electrical energy. What energy? Electrical energy. It stores. And how it stores electrical energy, we are going to see here. So a basic capacitor is like, suppose that you have a conductor which has the plus Q charge. It can be of any shape. I will draw it a circle. And you have another conductor who is a negative Q shape, such that the magnitudes of the charges are equal on both of the conductors. So any two conductors whose opposite charges and held apart at some distance can act like a capacitor, because you know that they have a very type of electric potential energy between them. You study the formula of the electric potential energy between any two objects. So between these two particular isolated conductors, there is an electric potential energy between them, and that is a typical example of a capacitor. So it can be of any shape. There is not a perfectly defined shape of an capacitor. It is an arbitrary manner you can define of any shape. And this is a typical example of this. So their electric field line is like outward, and there's electric field line is like inward, and it forms a capacitor there. Now, one more thing is there. Suppose that you want to add some extra Q amount of charge on a capacitor. So if you want to add extra, suppose that extra Q charge to these capacitors, you all know that it also increases its voltage between the two terminals. And it means in a capacitor, the charge Q is directly proportional to your voltage. It means the higher you want to increase the charges on the capacitors, the higher the voltage also increases between these two particular isolated conductors. This is VA and this is VB. VB minus VA increases, or VA minus VB increases if you increase the charge Q. It means Q is directly proportional to the potential difference V between the two isolated conductors. Now if there is a proportionality sign, we can generally introduce a constant there, which is q is equals to c v. You can think it like in a manner that voltage is directly proportional to the current. The higher the voltage, the higher the current is. And we also introduced there is a constant sign here, which is called the resistance, which is V is equals to Ri. Just like this, in this situation, the higher the Q charges on both these two particular isolated conductors, the higher the Q charges, the higher there is a potential difference between them. And if we introduce a constant sign, we get a very important formula in our capacitor chapter, which is this particular Q is equals to CV. Q is equals to C. This is a very, very important formula. Q is equals to CV, which relates the Q with V with a constant C, and what this particular constant C is. So this particular constant C is called the capacitance. What the heck this particular capacitance is, let's see here. Okay, what do you mean by this particular capacitance? So just like the capacitor is a property of a capacitor to store charge, that how much charge can it stores. And we all know that the capacitor store the electrical energy. It stores the electrical energy in the form of charges. In the form of charges it stores. So how much charge can a capacitor store is tells us by the particular capacitance. Capacitance tells us how much charge you can store on a capacitor. So now we can rewrite this particular equation as C is equals to Q by V. So in our next video, we will talk about that C is not only dependent upon the C is dependent upon different types of quantities like the distance between the capacitors and the area of the capacitors also. But here, one point you have to remember that C is not dependent upon Q and V, not dependent upon Q and V. Remember that C is not dependent upon Q and V. Just like when you write that resistance is equals to, so resistance is equals to V by I. Resistance is not dependent upon voltage and current. It is, I think, R is equals to rho L by A. I didn't remember the exact formula, but I think, yeah, this is the formula. So it is equals to rho L by A. It is not dependent upon voltage and current and all that things. So remember that just like this, capacitance is also not dependent upon the Q and V. Capacitance do not depend. It means the ability to hold charge of a capacitor is not dependent upon the charge it holds and the potential difference between them. How? So if you know that Q are directly proportional to V. So if I increase the charge by 2Q, there is also the increase in the voltage between them, such that this 2 and 2 will cut out and you will get the ratio between Q and V constant. And that's why that particular C is not dependent upon Q and V. Hope that you understand that the capacitance is not dependent upon the Q and V, just like the resistance is not dependent on voltage and current. So let's define what is the unit of the capacitance. So capacitance unit is farad. It means suppose that I put 1 coulomb charge and 1 volt, then it is equals to 1 coulomb sorry 1 coulomb per volt. What is the meaning of this? So let's understand. There is a very good meaning behind this 1 coulomb per volt, and it can be also written as 1 farad. 1 farad. Okay, now let's see the meaning of 1 coulomb per volt. There is a very good things and I like it very much. So what is the meaning of 1 coulomb per volt? So let's see, let's see with an example that there's a conductor. Let's say there is a spherical conductor with a positive charge. Okay, so if there's a spherical conductor with positive charge on its surface, okay, just like this here, and you want to bring the extra positive charges from infinity. So let's just define this point infinity, and you want, this is the plus Q charge. Okay, so you want to take this plus Q charge onto the surface of this particular positive conductor. You know that these positive and positive charges repel each other. It means you have to provide you have to provide the extra energy, sorry, extra to provide the work, external work, to just place this plus q charge on this particular isolated positive charged conductor. So now you'll provide the plus q charge, you have to do work. And again, if you want to provide more plus q charge, you have to do more work as the potential of this particular spherical conductor increases. So if there is a potential V and you transfer one more charge to this particular, one more, let's say 1, 2, 3, whatever, the charge to this particular positive conductor, its potential now is V dash, where V dash is greater than the V. And you know that when you increase the Q, the V dash also increases. The potential of this particular spherical conductor also increases. And just like when you want to place more and more charges on it, the potential increases. If you want to place more plus q charge, you have to do more work than you have to do to move the this particular. If you there is a first and you have to put this particular second, then the work done in moving this particular one charge is less than this. Because if you put down this particular plus q charge on this particular spherical conductor, the V, which is the potential of this particular spherical conductor, increases. Now you have to do more work than before. It means you have to provide more work. Suppose that there is a W work in this. Suppose that it takes W work to place that plus q charge on a conductor, and W dash to this second. So W dash is greater than the W. You have to provide more energy because its voltage or increases in more amount significantly. So if for any particular capacitor, the meaning behind 1 coulomb per volt is like this. Suppose that you have a capacitor there. So if you provide 1 coulomb charge, I am taking a single charge here, but let's see if I have to take a very high amount of 1 coulomb charge. So if I take 1 coulomb charge to a spherical positive conductor like this, there is an increase in the voltage of the spherical conductor by 1 volt. Understand? So let's see another example, that let's say you define capacitance as 21 coulomb per volt. What is the meaning of this? The meaning of this is that you have to provide 21 coulomb of charge, and if you provide 21 coulomb to the charge, then the voltage of your spherical conductor will increase. So which will be easier? Suppose that there is a capacitance C is equals to 21 coulomb and one has this C is equals to 10 coulomb per volt. Which you will prefer? Think deeply that 10 coulomb per volt, which means you will provide 10 coulomb charge to this particular spherical conductor, then there is an increase in 1 volt, and then again 10 coulomb, then again 1 volt. So in this particular case you have to provide more and more energy. But in this particular condition it is very good, because when you will take 21 coulomb charge, then there is an increase in 1 voltage. Then there is increase in 1 voltage when you take the 21 coulomb charge. So which is good, this 21 coulomb or 10 coulomb? Obviously 21 coulomb, because in this situation if you do 21 coulomb, then there is an increase in 1 voltage. But in this situation when you do 10 coulomb, then there is increase in 1 voltage. So this particular situation, this particular capacitance is very good. I hope that you understand the meaning, that what is the meaning of 1 coulomb per volt. The meaning is that when you provide 1 coulomb charge to the spherical conductor, there is an increase in voltage by 1. Just like this, if it's a capacitance, let another example. Let's say if there is a capacitance like there, if I assume capacitance as 10, okay, 10 coulomb per volt. What is the meaning? Sorry, 10 no. Let's another example. Let's say 2 coulomb, 3 coulomb. Okay, 3 coulomb. What is the meaning of this? The meaning of this situation is that the potential of a conductor increases by 1 when you provide the 3 coulomb charge to that conductor. It means you provide 3 coulomb charge to the conductor, its potential become more than its potential increases by 1. Then again you will provide then a 3 coulomb charge, then again its potential by 1. So there is a loss in this particular situation, that this capacitance is low. It means it cannot hold very much charge at once. But this particular situation, that C capacitance is equals to 21 coulomb per volt, is very good. And if there's a capacitance whose capacitance is, let's say, 50 coulomb per volt, yes, if this capacitance is 50 coulomb per volt, it is also very, very good, because now you will provide 50 coulomb charge to the capacitor, then there is an increase in only 1 volt of its potential, and you have to do the less work. So this is the meaning of behind the 1 coulomb per volt and one. And what's the 50 coulomb per volt meaning? What is the meaning of 10 coulomb per volt, 21 coulomb per volt? I hope that you understand this. And if you can't understand this particular thing, you can mention in the comment section. I will make your doubt clear. Now you have to understand that what's capacitance. You understand what is capacitance is. What is the capacitor? So it is easy that capacitor is a device which stores electrical energy in the form of charge. Okay, and we all understand that what is capacitance. So capacitance is a constant and does not depend on Q and V, charge and voltage, because if we increase your charge by 2, there is also significantly increase in the voltage by 2 and the ratio becomes same. Just like in this particular situation, if you increase your voltage by 2, there is also the increase in current 2, and this 2 and 2 will cut out, and there is a ratio is a constant. Just like this, the capacitance is constant for a conductor. For a capacitor, the capacitance is constant. Hope that you understand that what is capacitance, what is the meaning of 1 coulomb per volt, because this is very sensitive thing, 1 coulomb per volt, and I like this very much. Hope that you understand this. Now moving to the example of the capacitor, which is a parallel plate capacitor. Now we are in a position to discuss about the parallel plate capacitor. So what is a parallel plate capacitor? So it is like this. There are the two sheet. Just like this. There is a two sheet. The plates, you can say that in a more appropriate manner. So one plate is generally plus Q charged and second plate is negatively charged, such that their magnitudes are same. If there is an equal number of protons and electrons in both of the sheets, and the distance between these particular plates is very small, which is d, very, very small, d, and there is an assumption that we have to made that the distance between these two particular plates is very small. It means the height of, let's say, this length of this particular capacitor should be very, very much greater than the distance between these two particular plates. So these two particular plates acts like a capacitor, has equal charges plus Q and minus Q. So now we are going to find out the capacitance of this parallel plate capacitor. So if there is a parallel plate capacitor is like this, so how I can find out the capacitance of this? And we are using the Gauss law. So let's say this is positive, 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 positive. This is negative, 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 negative. Okay. How I can find it? So let's see. We define, let's see the Gauss law. What is Gauss law generally? So if you remember that Gauss law, that integral of E into dA is equals to Q divided by E naught, and there is in this particular sign, okay, which is they call the closed integral. Now the electric field here is constant, just pick it out, electric field outward, and this dA is equals to Q divided by E naught. Okay, now you know that I have imagined they are the parallel plate capacitors. So that's the dA will, generally the integration of dA will become A, which is EA is equals to Q upon E naught. And you know that there is an electric field lines that are going like this. There is an electric field line. Now we can see this, and when we rearrange the terms, then we can find out the electric field. So electric field is equals to Q upon E naught, and here A, where epsilon naught is a constant, D. Okay, now here electric field is equals to Q divided by E naught A due to this particular positive plates. Let's say we have defined the electric field due to this particular positive plate, which is Q divided by E naught A. Now we have to find out the capacitance. How we can find it? So remember that we have defined a very good formula, that VB minus VA is equals to the negative of the line integral of the electric field. the path of integration that you are choosing. And we choose the path of integration generally from this positive to the negative plate. From the positive to the negative plate. So line integral of our electric field from whatever path we are choosing. So we are choosing from the positive to the negative direction, integration path. Now here this is our VB, which is VB is the negative plate potential and VA is the positive plate potential. And you know that VB has less potential. VB has less potential than VA. It means this VB minus VA can be written as, so I will substitute in this here, that VB minus VA, let's substitute this negative V. Why negative? Because here VB is smaller than VA. So obviously this will be negative. So I can think that this is equals to the negative of the V is equals to negative of the electric field, putting the value of electric field as, putting the value of electric field as Q divided by the E not A, and here, here the DL, here the DL from positive to negative. I'm saying this that we are going to do the integration from positive to the negative plate. Now this negative and negative will cut out, and this negative, this is not positive, I have cut out these two things. Then we can find out that the potential is equals to Q small q divided by E naught and here A, and the integration of dl. So the dl is what? This particular path we are choosing. So this distance is d. It means the integration of dl is d. So the potential is q d E naught by A. So this is the potential difference between two parallel plate, and they act like a capacitor. So this is a very important formula, and from this formula we are going to derive the capacitance of our parallel plate. Now we have studied that V is equals to QD E naught by A, where A is the area of a capacitor, area of a plate. Okay. Now we are going to derive our energy. We are going to derive the potential energy. So now the potential energy of the parallel plate capacitor, how I can find it? Potential energy, how I can find this? So let's see here. Now we all know that potential energy U is equals to the change in voltage. I can change in voltage, or let's say V, into the charge Q, because we all know that voltage is work done per unit charge, or the more appropriate voltage, V is equals to your U divided by Q. So now in this particular situation, now I'm going to do a very important thing, that how I made a parallel plate capacitor. So I have two neutral plates. See this, because I'm going to a very different approach to find out the potential energy between the two parallel plates. So there's a two parallel plates here. I will draw it like this manner. Okay, so there's a two parallel plates. They're electrically neutral. How I can make it positive and negative charge? Because I have said before that the charges on both the plates are equal in the magnitudes. So if I connect it with a circuit like a battery, and connect it with the circuit, and transfer, if this is an electrically neutral, I will transfer the negative electrons from any of the plates to the, suppose if this is A plate and this is B plate, so I will transfer the negative free electrons, because this is a conductor, and a conductor there is a free electrons. So I will transfer the some of the electrons from A to our B. So you all know that if I transfer this particular, let's say there is an electrically neutral, it means if I define that there is an equal number of plus Q charge and minus Q charge, or I mean to say there is half positive charges and half the negative charges on this particular conductor. So if I transfer this negative, if I transfer this half of the negative charge to this particular B plate, then this particular our B plate, or let's say a conductor, has minus q by 2, as it's the charge magnitude, and there is positive q by 2, positive q by 2. If I think so that I will transfer this, but I will just explain you to understand the analogy that there is a total number, because if you add this will become 0, because the total charge is 0. So if there is a total number of q by 2, then this become positive q by 2, because it transfers the negative q by 2 charges onto this particular plate. Remember? Then this will become equal in magnitudes and positive and negatively charged. Okay, so now how I am supposed to derive the expression using this particular thing? So same applies for our now system. Let's say I will just going to do the same thing. But here I will put down not charge as q by 2. I will put the charge as 2q and then divide it as q1 plus q to understand it, to get it into my equations. Because if I plug the value of q by 2 and minus q by 2 to find out the potential energy, then I think it will be very difficult to find out. So I want to put on the analogy on this particular charge. Okay, so if I have the two parallel plate capacitors, like I think here, yes, this and this two parallel plate capacitors, this is q. Let's say they have 2q charge in the magnitude, and again 2q charge in the magnitude. It means if this is A and this is B, this is a 2q, it means there's a positive q charge and the negative q charge in an equal amount. And same goes for this particular isolated conductor. It is positive q and negative q. So